Hello students, in this video I am going to explain you the principle of potentiometer, comparison of EMF of two cells and determination of internal resistance of a cell. It is an accurate instrument for measuring EMF of a cell. It has a long wire of uniform cross-sectional area as you can see from here. The two ends are connected to a battery through a rheostat and a tapping key. Let us start. Potentiometer is an accurate instrument for measuring the potential difference between 2 points in an electrical circuit. The wire is connected between the terminals A and B. The A is connected to the positive terminal of the storage battery, that is E1. And the other end B is connected to the negative terminal of the battery through a rheostat and a key. The current flowing, that is this, the current flowing in the wire is varied by the rheostat only, and the EMF of a cell in the secondary circuit is applied or connected through a galvanometer and then to a jockey which is sliding on the wire AB. The positive terminal of the cell is connected to A and the negative terminal is connected through galvanometer to a jockey which is slided along the wire, and current flows from A to B. Therefore, potential difference falls continuously from A to B, and this is the principle of potentiometer. That is, the fall of potential across any portion of the wire is directly proportional to the length of that portion of the wire which is having uniform cross-sectional area. Let the area of cross-section be represented by A and rho be the specific resistance of the material of the wire. If V is the potential difference across the portion of the wire of which the length L is considered, whose resistance is R, then by using Ohm's law, V is equal to IR, and R can be written as rho L upon A, where if we look carefully, the current flowing through the wire AB is a constant. Resistivity or specific resistance of the material of the wire is again a constant. Area A is a constant, so the potential difference is directly proportional to the length. That means if we put down all these constant values together, that is represented by K, which is called as the potential gradient or fall in potential per unit length of the wire, and V is proportional to length L. Now let us use this principle of potentiometer to compare the EMF of two cells. Let the two cells are represented by EMF E1 and E2, and they are connected to the potentiometer in the manner shown in the circuit. Their positive terminals are connected to the positive terminal of the battery, that is at point A, and the negative terminals are connected to a switch at terminals 1 and 2, that is a two-way key, and the common terminal 3 is connected to a jockey through a galvanometer like shown in this manner. Now let us insert a plug between terminals 1 and 3, that is, we are connecting the terminals 1 and 3 in this manner. That means the first cell having EMF E1 is in the circuit. Now let us search the balanced position on the wire. Let that balanced position, or when the galvanometer is showing no deflection, that position is represented at N1. So the length of the wire from A to N1 is represented as L1. Therefore, according to the principle of the potentiometer, the EMF will be equal to K times L1. That is where K is potential gradient of the wire. Let us mark it as equation number 1. Now, remove the plug from 1 and 3 and place the plug between 2 and 3 terminals. Let us again see. That means I am now putting the plug instead of between 1 and 3, I am placing the plug between terminals 2 and 3. That means now E2 is in the circuit and E1 is no more in the circuit. So, repeating the same procedure, that is, we are searching the null position of the galvanometer on the wire AB. The position is found at N2 and we have noted the length of the wire. Let it be represented as L2. In the similar manner, the EMF of the second cell E2 will be K times L2. Dividing equation 1 by 2, we have obtained the ratio of the EMFs of the two cells E1 and E2 is equal to L1 upon L2. That is, we have compared the EMFs of the two cells and they came out to be the L1 upon L2. Now let us determine the internal resistance of a cell using potentiometer. Here, the internal resistance of a cell having EMF E is represented by small r. A constant current flows in the potentiometer wire and the position of the jockey is searched again on the wire, at which the galvanometer shows no deflection. Let that position be again represented by N1. At this position, when the galvanometer is showing no deflection, then that length is represented as L1. The EMF of the cell when no current is drawn from the cell will be equal to K times L1, just by the principle of the potentiometer, where K is the potential gradient of the wire. Now, let us take a resistance from the resistance box. This is the resistance box placed. Earlier there was no key in K2, so that part was not in the circuit. Only this part was included in the circuit. This branch was included. Now we are inserting the key and this resistance is included. So again we have to search for the position of the jockey at which no deflection is shown by the galvanometer. Let that position is represented by N2 and the length will be L2. As current is drawn from the cell, it will become terminal potential difference V. So here it will not be EMF because now we have considered the resistance. So it will become terminal potential difference. So V is equal to K times of L2. Again dividing the two equations, we have obtained E upon V is equal to L1 upon L2. Also we are aware that the EMF of the cell can be represented as I times capital R plus a small r, where small r is the internal resistance of the cell. And by Ohm's law we are aware V is equal to IR. Putting these values, that is the value of current I in the above equation, that is here. So we have obtained this equation. Rewriting this equation in order to calculate the internal resistance of the cell, it becomes equation number 4. So this is one of the expression for internal resistance of the cell. Another expression can be written by putting down the value of E upon V from equation number 3. That is, small r is equal to, internal resistance is equal to R into L1 upon L2 minus 1. See, the fall in potential across the potentiometer wire is greater than the potential difference to be measured. That is, we have to be careful while adjusting the edge of jockey. It should not be rubbed, otherwise the area of cross section may also get changed. Also, the current should not pass for a long time because it will heat the wire and the resistance will also get changed. Also, there is one more question, that why do we use a potentiometer when we have a voltmeter to measure the potential difference? Because the reason is that the EMF of a cell is very accurately measured by this potentiometer, because it does not draw any current from the source and it is highly sensitive instrument. Now let us practice one numerical. A potentiometer is used for the determination of the internal resistance of a cell having EMF 1.5 volt. The balance point of the cell in open circuit is at 76.3 centimeter length of the wire. When a resistor of 9.5 is connected across the cell, the balance point shifts to 64.8 centimeter, and we have to calculate the internal resistance of the cell. See, when the cell is open circuit, as it is given that E is equal to 1.5. So when the cell is open circuit, the EMF is equal to K times the length, that is K is potential gradient. From there we can have equation number 1. After that, the balance point is obtained when a resistor of 9.5 ohm is connected across the cell, and that balance point is 64.8 centimeter. So when a resistance is included, it will become terminal potential difference. So it is V is equal to K times the length L2, that is 64.8 centimeter. Let us mark it as equation number 2. Now dividing the two equations, we have obtained E upon V is equal to 76.3 upon 64.8. And the internal resistance formula we are aware from our earlier studies, that R is equal to capital R, that is the resistance, into E upon V minus 1. Putting down the value of E upon V from above, we will get this expression, and R is already known to us, that is 9.5 ohm. So the internal resistance is calculated as 1.68 ohm. Let us attempt one more numerical. Here 10 meter long potentiometer wire carries a steady current. A 1.018 volt standard cell is balanced at a length of 850 centimeter. Find the potential gradient along the wire. When we need to calculate the potential gradient, we are aware of the formula that the EMF is equal to K times L, where potential gradient K is equal to E upon L. E is already given to us, it is 1.018, and the length is 850 centimeter. Simply dividing it, we will get the answer for the potential gradient. Now for the maximum EMF can be when the whole length of the potentiometer wire is considered. That is, V is equal to K times L, where L is 10 meters. So instead of 10 meters, I have written 1000 centimeter, because this answer was also in volt per centimeter, and I have taken the potential gradient from part 1 only. So putting down the value as K into L, where K is the potential gradient multiplied by the length, we will get as 1.19 volt. That is the maximum EMF that can be measured from the wire. Thanks for watching. Please like, share and subscribe.